So the next thing we're going to be looking at is linear approximation and differentials. And both are similar in terms of the execution, but just the concepts are, they're both very similar in the idea. And the idea is that we're going to use a linear approximation to estimate a value, to say, like, I'm going to look at it as a straight line near a point that I know. And we can either describe it as a differential or as a linear approximation. So as an example, say I'm trying to estimate the value of a function, say around here. But I only know the derivatives and stuff about here. Well, I can use a linear approximation to estimate that value, say here. Or I can look at it similarly as a differential, like a change in x, a dx, and a dy. And so that's the basic idea of it. That's why they're kind of very related and very similar ideas. So as an example, given p of 0 is negative 67, and I believe there should be a prime there. Let me just double check the... and p, yeah, one of these should say probably p prime is 5. So say it's like this. This is supposed to be the derivative. So say I know the value of the function and the value of the derivative. Approximate p 110. So there's two ways you can do this. I'm going to do this both as a linear approximation and as a differential, just to show you this. The first thing we do is we say, well, I can create a tangent line at this point. And so it'd be y minus y naught is equal to m x minus x naught, right? That's the slope point form I would use for any equation. Well, my point is 100 negative 67. So it'd be y minus negative 67 is equal to m times x minus 100. And then we would say the slope is the derivative at that point. So it's 5. Okay. So this would be y plus 67 is equal to 5 x minus 100. Or we would say y is equal to 5 times x minus 100 minus 67. Okay. And so if I were to use a linear approximation, I would say y of 110, for example. I plug in 110 here. It would be 5 times 110 minus 100 minus 67. And I would get 5 times 10, that's 50, minus 67. And that's equal to negative 17, right? Okay, so that's the way we do it with linear approximation. Differentials is very similar, but differentials is just like thinking about it a little differently. We're basically saying, okay, we're going from the point 100 to 110. My change in x is 10, okay? What is my change in y equal to? Well, my change in y would be like this derivative, p prime of 100, is really equal to the dy dx. It's the slope, right? It's the change in y over the change in x. So my dy, my change in y, which is what it would be, equal p times the derivative of 100 times dx. And the way we would say this, if my change in x, my dx, is 10, and this is the derivative is 5. If my change in x is 10, my change in y is going to be 50. 50 times 10 would be so 50 would be equal to 5 times 10. And so since I start at negative 67 here, negative 67, that means I go up by 50. So I add 50 to this, and I end up with negative 17. And that's where I'm at. So that's the differential approach to it. And I'm going to use interchanging between the things. I think the differential is a better intuitive understanding of what's happening. Linear approximation is fine. That's actually what they'll do on the AP Calculus exam, but I think thinking of them as differentials is also useful because it's useful if you study physics or other more complicated calculus down the line. So for number 2, knowing that f of 1 is 25 and f prime at 10 equals 5, which approximation using linear is likely to be most accurate? Oh, this should be f of 10, by the way, is equal to 25. Which is likely to be more accurate, and explain your reasoning. Well, you see, the tangent line approximation is only really good when it's better the closer it is to this point. Because if I'm very far away, like if I were to approximate this value and I use this tangent line is good for approximating nearby here. But you see, the further I go away in the x direction, the bigger the error is going to be. So that's why f of 10 plus 1 is the most accurate, because I'm closer to 10, and so this tangent line approximation, while introducing some error, is a small amount of error compared to when I'm very far away from there. for like f of 20 where I'm like much further away. Okay. So given h of 0 is 17, h of 2 is 29, approximate h prime of 2. This is approximating a derivative from 2 points. And so this is kind of the reverse idea, is to say, well, if I know h of 0 is 17 and h of 2 is 29, and I wanted to estimate this derivative here, like the tangent line slope, I can estimate it with the secant line slope. It's not perfect, but it's pretty close. So I would say h prime of 2, you could say approximately equal to h of 2 minus h of 0 over 2 minus 0. Like I said, it's the only slope that's a good approximation. And again, we're just simply using a linear approximation to approximate this value. So this would be 29 minus 17 over 2. That is 12 over 2, and that's equal to 6. Okay. Thanks for watching. If you're looking for more examples, go to my website. In there, I have free access to over 400 calculus questions that I solve and I show you step by step. So if you're interested in seeing more, please check out my website.